But with that, like, it's a great pleasure to have Professor Zach Manchester here to give a seminar talk. So Zach is a assistant professor at CMU, where he's doing a lot of interesting and inspirational work in like robot locomotion and essentially like contact rich optimization, planning and control. He had a PhD degree in aerospace engineering from Cornell, and he was also a neighbor before he moved to CMU. He was at Harvard working with, I think, Scott Condersama as a postdoc. And then he worked at Stanford, NASA Ames, and analytical graphics. He has worked on several like satellite missions with NASA. He got like a NASA Early Career Faculty Award in 2018. And as you will see, like, he's doing a lot of interesting work in some of the most challenging problems in robotic locomotion, spacecraft guidance, navigation, and control. So we look forward to like hour-long interesting discussion on all of these topics. So with Zach, the floor is all yours.
All right, thanks so much for the intro, and yeah, thanks guys for hosting. So yeah, I guess I've been on sort of maybe a 5-6 year odyssey where as you alluded to, I took a postdoc with Scott Kindersma, who was at Harvard at the time and now is kind of leading the controls group at Boston Dynamics. And prior to that, I was a space guy, an aerospace guy, still doing control stuff. But when I got into the robotics space, I kind of like was exposed to the fact that contact dynamics are, a whole rabbit hole of complexity and challenging challenges everywhere, and it became kind of an obsession. So this is a bit of a story of that obsession and kind of where we're at with it now. So just as a little warm-up thing, and for kind of some motivation and some of where my background is, I was actually at JPL last week, and my kind of first love is space exploration. So like this is one of my favorite robots, right? I got to see this guy, I guess the spare of this on Friday in the Mars yard at JPL. This is the Curiosity rover. This thing's been up on Mars for 10 years now. And in 10 years, it's gone almost 30 kilometers, which sounds really impressive, right? Covering 30 kilometers on another planet. It's an amazing technical feat. But if you divide those numbers, it sounds a lot less impressive. It works out to about 7-8 meters per day of driving that this thing does. And, you might ask the question, why? Why is it so limited? And it turns out the answer to that is this, which again, I was just there on Friday. It was very cool to be there in person. But at JPL, they have this thing they call the Mars yard. It's basically a giant sandbox where they have all kinds of boulders and rocks and things like this and shovels. And what they do there is they have a replica of the rover, and they basically, they have 3D imagery all around the rover on Mars. They try to recreate the landscape around the rover in this Mars yard, and then they practice driving around in the exact same, as close as they can make it, terrain, and figure out exactly how to drive the rover. And then once they figure this all out, they basically uplink the commands. So there's very little autonomy, I guess. They have worked on autonomous driving, but whenever they get into more, interesting scenarios, this is how they do it. It's painstakingly, kind of hand engineered. They figured it all out, and then they, uplink everything. And you can kind of understand why. It's very high stakes, very expensive, right? But the fact remains that it's a major bottleneck to covering more ground and doing more science. And ultimately, like, if we're talking about inspiration, this is another place I like to go for inspiration. Watching animals that navigate these things, and I love watching mountain goats. They're able to traverse insanely steep terrain, take full advantage of all the available friction and the dynamics of their bodies, and navigate these really, really crazy things to a degree that we're just completely incapable of right now in robotics, right? So I think this is the bar, right, that we should be aiming for. Okay, so that's kind of in some inspiration. And then kind of the first part of the talk is really a philosophical thing for me as far as how I look at all these things. And I guess it's really a worldview for me. In summary, everything is optimization. And so I'm going to try to argue that pretty much every piece of the stack here, from low-level dynamics simulation through to control at the top, planning, each of these pieces can be posed as an optimization problem. And maybe that's a good idea, and kind of walk you through that. So first off, I think nobody will find it a surprise that you can write down control problems as optimization problems, right? We've been doing optimal control forever. It's been highly successful. And so, the gist of this is you have a model of your robot where you have a dynamics model, x dot equals f of xu, which, you can get a bunch of ways from f equals ma to, sophisticated multi-body dynamics things. Then you have constraints, maybe on your actuators, maybe, joint limits, all this kind of good stuff. You write all that down, that's your model. Then you write down what you want your robot to do in the form of an objective function. So this can be something like, minimize fuel use or energy cost, minimize time to get to a goal. At the end of the day, this is really encoding the behavior you want, right? And it's a bit of an art to write this down, but if you do this enough, you get pretty good at it, and you can kind of pose these problems pretty nicely. And then you can get your computer to solve it, and out pops, interesting behaviors that can take full advantage of the dynamics, respect joint limits, all this good stuff. Also, maybe not so surprisingly, we can do state estimation as optimization. And it also looks a whole lot like that trajectory optimization problem we just saw, the control problem. There's basically, you get a least squares loss instead of like your maybe more general objective function. And then you have a very similar model of your robot. It turns out the only difference is you end up with this noise term in place of your control inputs. Otherwise, it's basically the same problem, and they look really similar. Okay, so state estimation, also not a super surprising. And there's a long history of, kind of duality between estimation and control that probably a lot of you guys have heard about. The one that's a little weirder that is maybe slightly more surprising, but not too surprising if you've taken like a, upper level graduate physics course and learned about variational mechanics. So we can actually model physics as optimization as well. And it's, once again, super similar and essentially looks like a trajectory optimization problem. So if we kind of look at this is the action integral, also known as Hamilton's principle, this principle of least action. And this action thing, what we've got in here is the Q of t is the pose trajectory. And so Q dots, basically the velocities. And this L thing is the Lagrangian. And the way to think about this, if you kind of stare at this for a second, think about the pose trajectory, the Q of t, think about that like your state vector in the control problem. And then Q dot, think about that like your control inputs basically. And then you can think about your Lagrangian inside the integral as your stage cost or one-step cost. And then the S here is your cost function. And if you kind of think about everything that way, this essentially, again, boils down to a trajectory optimization problem. There's a long history here. This isn't like an original thing, right? But where this gets interesting and where I think there's fun to be had that maybe is a little less standard in the robotics community, you can take this action thing. If you learned about this in grad school, what you usually do is take this thing and then try to take some kind of variational derivative, minimize this thing analytically. And if you do that, basically what comes out of that is the Euler-Lagrange equations and like all the usual dynamic stuff you're used to. And traditionally, when you learn this in like a physics class or advanced dynamics class, that's what happens. You do optimization here in continuous time, and then you get Euler-Lagrange equations, and that's where you live forever. But if you kind of take this optimization problem more seriously and really think about this as the fundamental object to deal with, you can, and if you have some inspiration from doing numerical optimal control and solving like trajectory optimization and MPC problems, you might think about directly minimizing this thing with respect to the trajectory, like you would in optimal control. And so you can discretize that action integral thing, do this in discrete time. And now what you have is like a pretty standard nonlinear optimization problem, exactly a trajectory optimization problem, in fact. So this idea is kind of cool. It turns out this is a much more recent idea. This dates back only maybe 20 years or so to the early 2000s and was really pioneered by Jerry Marsden, who's like a famous applied mathematician at Caltech. And a couple of his students are still playing around with this stuff. When you do this, what turns out what happens, it's basically discretize first, then optimize, rather than the classical way, which is optimize in continuous land. And then you kind of then use a Runge-Kutta method and discretize that. So that's one way to think about it. It's also super closely related to collocation methods and optimal control. And there's lots of cool things about this. These things are called variational integrators. They do cool things like preserve momentum and energy, and that's why math people care about it. But there's a more kind of nuts and bolts practical reason why I think we should care about this stuff in robotics, which is now that I write this down this way as a more or less standard optimization problem, and I think about it like a trajectory optimization problem, I can now think about adding additional constraints to it. And in particular, for thinking about contact dynamics, sorry, things are being weird, I can throw a constraint like this in here, this being a gap function or sign distance function, phi. And essentially what I'm doing here is saying that so like think about a brick and Q's the pose of the brick. I can put a constraint on here that says the brick's not allowed to go through the floor, that its like height has to be greater than or equal to 0. And if I do this and I solve this in the normal way with like a constrained optimization solver, all of a sudden what you get out of this basically for free is impact dynamics. And unsurprisingly, like the Lagrange multiplier of this constraint ends up being the contact impulse or force, and everything more or less works out like you'd expect. And it turns out if you look at this, this is very closely related to time stepping methods, like the classic Stewart and Trinkle kind of stuff, if you're familiar with that. It turns out this is a sort of strictly, I would argue, strictly better and more accurate version of this. And to get from here to like the Stewart and Trinkle time stepping stuff, you end up making a bunch of additional approximations and linearizations in certain places. So this kind of is a little bit more, I'll say, like accurate or principled way of getting at time stepping methods. So that's impact dynamics. The next piece of the puzzle is Coulomb friction, if you're worried about manipulation and walking kind of stuff. And it turns out this is also an optimization problem, a little bit different flavor. This is the maximum dissipation principle, if you've heard of this. Essentially says that the friction force B that you get is the one that minimizes the instantaneous rate of change of kinetic energy. So this is dissipation. So if I write down the kinetic energy and say I want to make E dot, like the dissipation rate, as negative as possible. I want to suck out the most kinetic energy as possible. That's what friction's doing, subject to this constraint down here called the friction cone constraint. And this says that basically the B has to be less than or equal to mu, some friction coefficient, times the normal force, which we call lambda here. This is kind of a generalization of like the high school, mu times the normal force friction idea to 3D and stuff like that. But yeah, so this gives you Coulomb friction. You plug in everything, you minimize, out pops Coulomb friction. And then the last one, which is actually the one we've been working on the most in the last like year or two in my lab, that's been pretty interesting, is collision detection. So it turns out, if you're familiar with how this stuff's usually done in physics engines and video games and things like this, there's a lot of work in the computer graphics community going back decades on this problem of detecting when objects are in collision, and most of it focuses on convex polytopes. So basically, like 3D versions of polygons, like things with lots of faces and edges and things like that. And the classic algorithms for solving this, which are fast and very sophisticated, there's a pretty standard one. It's called GJK, or enhanced GJK, that you'll see a lot. But all these methods, essentially what they end up doing is kind of traversing the nodes and edges of the polytope in kind of a search kind of way, and checking a bunch of stuff. And they're very sophisticated, and they can prune the search space and be fast and all this good stuff. But at the end of the day, they're doing this kind of like discrete search problem. And the key issue with this is that it's not differentiable. So if you want to take derivatives of things in this sort of setting to do control, they're not going to give you nice derivatives. So what we've done instead, and we have a couple of recent papers in the last year on this stuff, it turns out, unsurprisingly, you can pose this collision detection problem for convex primitives. So pairs of convex primitives, any convex shape. So things like spheres, polygons, polytopes, pills, cylinders, cones, that kind of stuff. If you give me any pair of these kind of convex objects, turns out the collision detection problem for that is a convex optimization problem. It shouldn't be super surprising. Norms for distances are convex. These are convex constraints, or can be models as convex constraints, and you kind of play around and get a convex optimization problem out of this. There's a little bit of secret sauce to doing this well, and handling all these kind of weird cases that show up. Like if you have two objects in penetration, and you want to say what the shortest distance to separate them out again. There's all these kind of special cases that show up that make it a little tricky, but essentially we've worked all that out, and we've managed to pose this as a convex optimization problem that has always is a guaranteed solution. It's bounded, et cetera, et cetera. And the key advantage there is, now that we've written it that way, one, we can handle all these new shapes that are not just polytopes, and two, we can actually differentiate this and get smooth gradients out of it, which is pretty useful for doing control. Okay, so that's the sort of first part of the talk, which is basically anything you want to do around contact dynamics, modeling, control of state estimation, you can pose as an optimization problem. So if you're going to grant me that, the next part of the conversation then is how do we hook all that stuff together? So if I can model each of these pieces, control, dynamics, friction, collision geometry, whatever, each of these is an individual optimization problem. If I ultimately want to do something like, solve a big control problem, I now have to figure out some way to kind of wire all these individual optimization problems together, like nest them, and they're all nested inside each other and coupled in all these weird ways. So I have to find a way to hook them all together and then like jointly solve them. And so that's kind of the next part that we're going to get into, that we spent a lot of work on. And so as a brief kind of like, I don't know, aside, just to kind of talk about, the classic ways of doing this and some of the things that are hard about it. So here's that like kind of trajectory optimization thing. And as I've kind of already alluded to, you can do cool things with this. But one of the key assumptions behind almost every numerical method that we have to attack these things is that the dynamics, in fact, all the functions in here have to be smooth. Like I have to be able to take gradients, right? Because I'm always, at the end of the day, when I try to solve something like this on a computer, I'm always doing some version of gradient descent, Newton's method, right? And I need at least one derivative, often two derivatives for all these functions in order to, for me to like make progress with an optimization method. And so in the context setting, the dynamics are non-smooth when I have impacts and things like that. And then like these derivatives don't exist or they blow up and bad things happen, right? So there's a few approaches to dealing with this. One is the so-called hybrid approach, which is to pre-specify what are called mode switches in the business, but these are just the exact times when you're going to make or break contact. So you can imagine in a walking problem, this would be if I can pre-specify the gait. So if I have a biped, this is pretty easy, right? Left, right, and I can maybe heel toe, that kind of thing. But if I can pre-specify the timing and the ordering for all these contacts, then what I can essentially do is bake that into the optimization problem as a set of constraints, like they're a priori in there. This is what you have to do. And then I'm basically just optimizing over the smooth segments in between these impact events, say. And now I'm back to the sort of smooth problem I know how to solve. I've essentially removed, by pre-specifying, when these contact changes are going to happen, I can basically remove them from the optimization problem. And now life is good. And so this has been hugely successful. This is kind of, I would argue, the standard approach. And it's, kind of what, roughly speaking, what, these Boston Dynamics things are doing. And a lot of the quadruped videos you've seen are doing this kind of stuff. Again, you can do amazing things with this, super sophisticated things with this. But there's a key issue that if you look critically at like the blooper reel videos that Boston Dynamics puts out and many of these other guys, if you look carefully at this stuff, you'll notice that almost all cases where there's failures, and it's pretty obvious in this video, they come from unplanned contact events. So like in this video, you see the robot, clearly the plan involved it jumping over there without the foot touching the bar, right? And in this case, things are a little off, some errors in your state estimator, and the foot ends up grazing the box, right? And now it fails. And at the end of the day, the reason is these hybrid methods where you're assuming a certain contact mode sequence. One way to think about it is the controller is essentially running open loop on the contact modes. You've made this assumption on the modes are going to happen this way in this order, and these are the only parts of the robot that are going to touch the environment. And if online, due to disturbances or whatever, that's not what happens, and inadvertently the robot makes contact with another parts of its body, with the environment, this kind of thing, and you get a disturbance that way, the controller has no way of reasoning about that because you've baked that in as a prior essentially, and it just can't recover, right? So that's kind of the key issue with these hybrid methods. And in practice, a lot of the control stacks for these things end up with a lot of heuristics to do things like push recovery, where they just have like a laundry list of if this, then try this other thing, kind of heuristics for dealing with these scenarios. But the controller at a base level isn't really equipped to reason about this stuff. Okay, cool. So that said, there's this other set of ideas that have been around for a while too, and people have worked on these a whole bunch, going back at least a decade, a little more probably, called contact implicit methods. And the idea here is kind of what it sounds like. You're going to try to optimize over not just the state and control trajectories, but also the contact forces, and do the whole thing. And the idea here is now the controller can reason about these contact events, but again, because of the non-smoothness and the problems with differentiability, historically these things have been really fraught with challenges. You either kind of smooth out all the contact stuff to try to get those derivatives, but then your physics is not accurate and it doesn't work in the real world. And then if you try to crank up on all those stiffness parameters and make it more realistic, now you get really stiff dynamics equations. The ODEs become like really hard to integrate, and things start to blow up on you and you can't optimize again. So there's all kinds of numerical problems with this. And so essentially what I'm going to tell you about now is a way to sidestep the kind of severe numerical difficulties with this setup. Okay, and the overall sort of set of ideas here is what I coined this, and I don't know, this is kind of what we're going with to call this composable optimization. So like we kind of alluded to, right? Each one of these blocks you can pose nicely as an optimization problem. But if you want to do all of this all together to ultimately have a controller that can reason about all the dynamics and the friction and the collision geometry, you end up with a bunch of coupled nested optimization problems. And so how do you deal with that? How do I wire these together? So just to pick an example here, let's talk about the impact dynamics and cooling.
Can I ask one question if I interrupt you? Sorry. So for the Boston Dynamics example that you showed, so is that like a optimization problem? Like in the sense, like, is that a trajectory optimization problem? Like when the unwanted contact happened, or would that be like a estimation problem that the controller needs to know that something undesirable happened and now I need to recompute it? Like would CITO methods be actually more like robust to those things compared to the hybrid methods? So it would be like irrespective, we will need to have an estimator that tells my optimizer that, look, something weird happened and now you need to adjust according to that.
Yeah, so I mean, it's clearly a both problem, right? You have to know what's going on in order to act on it. But right now, the way these things work, and again, like BD doesn't publish this stuff, right? And so we kind of can infer some things based on public talks, in the last couple of years and stuff. But essentially, they're doing model predictive control, with some kind of, roughly whole body model of the robot. And it's this hybrid stuff where they're kind of pre-specifying contact sequences, and then they have some higher level stuff that's doing footstep planning and stuff like this, right? So in a situation like this, if they make contact, so the controller only is assuming that contact can only happen between certain parts of the robot's body and in the world at certain times and things like this. And I'd say, like, in that situation, if you had a state estimator that could infer that, what it would come down to, like, at the end of the day, with the hybrid method, the contacts are fixed in the model of the robot. So in that scenario, the robot thinks that only the hands are making contact and the feet are in the air. And so the control strategy, say the state estimator says, oh, I have a big disturbance here that I need to counter. The problem is that the controller, assuming that certain mode, right, which is baked in, says, okay, well, if I need to counteract this torque, I can use forces from my hands and maybe inertial effects of my body to do this. And it might respond a certain way without reasoning about the fact that the foot's actually touching. So it might like push with its hands and wiggle the body in a certain way to try to counter that disturbance. And given that the foot is in fact in contact, that'll have a very different net wrench on the body, right, than otherwise, right? So that's the sort of thing that happens. And you could imagine like designing a set of heuristics that says, oh, okay, I detected this thing. That means like maybe this other part of the body's in contact. And so now maybe I need to change my model and use this new, kind of like strategy to recover or something. And that's roughly what happens in a lot of the push recovery. There's a whole literature, right, on push recovery for humanoid robots and things like this, where they have strategies for lifting up a foot and pushing it out in the direction of the fall and this kind of stuff. But it ends up needing to be hand coded, right? And like you basically have to have like a library of heuristics for all conceivable scenarios, which is not, I guess, super satisfying.
Yeah, no, I totally agree. Thanks. Yeah.
Yeah, sure. And yeah, I guess generally, if anyone, feel free to like, interrupt and bug me during this. So it's not just me talking at a screen and by myself in a room. So yeah, I guess let's take the example here of, let's say we're just thinking about the dynamics and we have this impact dynamics problem, which has your kind of, rigid body dynamics and the collision constraints in it. And then we have the Coulomb friction block. So these things are coupled, right? Because the Coulomb friction force shows up in the rigid body dynamics, but then also the normal force, which is coming from the collision constraints, shows up in the Coulomb friction problem, right? So they're coupled this way. So there's variables that show up as, say, external parameters or problem data, so to speak, in one problem that are decision variables or optimization variables in the other, right? And so how do we hook these together? So the key idea that we use to attack this is this idea of a differentiable interior point method. So we use interior point methods to solve each of these problems. So each of the blocks in there, the impact dynamics, the collision detection, Coulomb friction unit, each of those blocks, we're going to write an interior point solver for. And in many cases, those subproblems have nice properties, right? So for example, the Coulomb friction problem is a second order cone program. It's convex. We know how to write nice interior point methods for these. So we write down a good interior point method for that problem. It's tailored for that problem. And then it looks like this, right? So we'll take this as a prototypical example, just to make life easy. So generic, minimize some function f of x and subject to some constraint, c of x greater than or equal to 0. And the idea here is we're minimizing over the x, and then theta are the other parameters that show up in the problem, right? So if we take the example of the Coulomb friction thing, the f would be minimizing the dissipation, the energy dissipation. And then the theta would be like the normal force that comes from the other problem. We're not optimizing over here. We're getting it from the other block, right? Okay, but the problem's solution depends on theta, right? Okay, and so in order to wire these things all together and jointly solve this whole thing, essentially what we need is the ability to extract gradients here of the solution with respect to the theta, right? If I change theta because it's coming from this other problem, how does that impact the solution of this problem? And so the way we do that, the interior point thing is you take this constrained optimization problem and you put the constraints into the objective with this log barrier term, right? And that looks like this. And this is very classical. We didn't make this up. It's been around 30, 40 years. And I guess the overall message here is that this is like a very standard thing to do. And it's, textbook optimization stuff, highly successful. And in fact, if you go solve a small to medium size convex optimization problem, this is the thing to do, right? This is the thing you will see in the textbooks to do. And the reason this works so well, you put this so-called log barrier in here on your constraint. And what happens is as the constraint approaches 0, the log function blows up, right? And so it prevents you, it's called a barrier because it prevents you from sort of crossing across the constraint boundary because it blows up to infinity. And the reason this works so well is that the log function is smooth, it's analytic, it's infinitely differentiable. And it turns out it plays super nice with optimization solvers, numerically speaking, right? So this works great with Newton's method. I can take all the derivatives I want, and I can get quadratic convergence and all the good things. And the way this works in practice is you have this kind of fudge factor rho here. This is sometimes called the central path parameter in the optimization literature. And in order to solve one of these problems, you start with it pretty relaxed and nice and smooth, like this yellow line, and then you crank on it as you converge. And in the limit, as you drive this up, it approaches this kind of brick wall, which is the exact solution to the problem. And so what you do is you start with it nice and relaxed, and each iteration you crank it down until you get to, whatever tolerance you care about. And you can get answers to full double precision, numerical precision with this kind of stuff. And there's all kinds of nice tricks. And there's like 30 years worth of literature on doing this. Okay, so the upshot for us is that once we've kind of put it in this log barrier form, it's smooth. And I can take this and differentiate it. And so we basically just differentiate that log barrier kind of version of the problem, the interior point problem. And now we can kind of use this implicit function theorem trick, and we can get all the derivatives we want, right? So basically we can get the solution, we're called the solution x of theta here. It's the solution of this problem, the x that, is a function of theta, effectively depends on the theta, and we can get this gradient or Jacobian matrix or whatever. And this basically lets us get all the derivatives of all those blocks and then hook them together into one big outer optimization problem. What else is there to say about this? Yeah, that's the essential idea. Yeah.
I think Matt has a question. Matt?
Yeah, so I can see this working for problems that are largely free space, like jumping around on blocks, but where it's extremely easy to find a feasible point right from the start, right? Your feasible point is that you just jump right up in the air and land at your goal. But for example, for something like a snake in a maze, finding a feasible point to start with and staying feasible, which implies a schedule for rho, is not so trivial.
Yeah, so there's lots to say about this, I guess. One thing to say first off the gate that is that There's actually pretty straightforward tricks for doing what's called infeasible starts with these interior point methods. And these are actually standard in the literature, and all the like standard solvers play these games. So you don't need a feasible initial guess, it turns out. I could talk more about how that works. It's like a basic, it's a little trick that you can play. So you don't need a feasible initial guess. And then as far as like the fact that you might have, sort of classic like bug trap maze kind of problems where it's really hard to find a feasible solution. These kind of optimization-based like trajectory optimization methods in general are bad at that, just period, right? And so the classical solution to this is to use some kind of like sample-based planner in a lower dimensional search space, like to find a feasible path through the maze, and then use that to warm start something like this that is now able to, now that it knows how to get out of the maze, it now basically needs to figure out the like whole body dynamics to kind of follow that path. So yeah, I don't know if things like that are useful, but I totally agree with you that like that sort of problem where you have a lot of constraints and dense obstacles, maze-like scenarios, these methods are really bad at without a bunch of hand-holding to at least get them like a classic version of this though that like does work out, right? That we've kind of played around with. You can do something like an RT or whatever in sort of just in XY space, to find a path out of the maze. And then once you have that, you can basically initialize the like, say, center of mass trajectory for a humanoid with that path. It doesn't have to be dynamically feasible at all, right? It doesn't have to walk. It can float in the air and just kind of levitate through the maze. If you kick it off with that, it'll figure out the rest, right? It can then go figure out the contact sequence, the joint torques, like everything else. So that's kind of, I'd say at a high level, you should use each tool for what it's good for. And like, there's complementary tools here. And you're absolutely right that these are terrible for something like a snake trying to get through a maze. If you were to just kick it off from scratch for that. Okay, cool. So, okay, so this is kind of the high level fuzzy picture where you can write down a solver for each block and then do this interior point thing and then get the gradients out. There's one more nugget in here that I think is worth mentioning. It's that I mentioned, with this interior point stuff, you can solve it to machine precision, which involves cranking that row way in. And in the limit, you get the hard, sort of like discontinuous hard answer. And that's not differentiable in the limit, right? And for sure, somewhere in the middle there's some numerical badness that can crop up. And so what we end up doing in practice is we can solve the problem, i.e. find X to high precision, but then we basically cache the solutions as you converge, and we return this derivative for a past solution with a more relaxed row. So basically, like one way to say it is you can kind of have your cake and eat it too. You can get the correct answer X, and then use a slightly more relaxed log barrier when you compute the gradients. And it turns out this works really well in a lot of practical scenarios, and it kind of gives you this best of both worlds thing. We can give you accurate contact dynamics, and we can give you smooth derivatives that are informative for planning and control stuff. Okay, so next up, what can we do with this? So I'll mention a few things we've done. One is we took kind of just the kind of dynamics, friction, collision detection pieces of this puzzle and stuck them together and made a simulator out of this. So it's like work from two of my PhD students over a couple of years who recently graduated. And at least one of them's at BDAI up in your neck of the woods now, Simon Leclièche. And so kind of the punchline here is, yet another robot simulator. Why do we need this? This was very much a research project, but kind of the answer is that we can get hard contact dynamics. So we solve those problems to convergence, to tight tolerances. Because of the way it's formulated, we get no interpenetration artifacts, no creep artifacts. Because of the nice integration properties of these variational integrators, we get like good energy and momentum conservation behavior. If it's a conservative problem, the dynamics are conservative, you get that. And you get good long-term energy behavior, like realistic energy and momentum behavior, even with, forced problems that are not conservative. And then finally, you could have this, have your cake and eat it too kind of thing where you can back off on the log barrier a little bit when you return the gradients. And so you can get kind of this nice best of both thing. One thing that kind of comes up here a lot is that, this is more expensive than most of the other kind of simulation methods that are used. And so you'll have to, you can't simulate as fast. I totally agree with that. It's absolutely true. The problems we're solving here are way more expensive to solve. We're solving these big, nasty, nonlinear problems at each iteration. But we can run these in real time, right? So this Atlas, this is full, all the degrees of freedom model of Atlas. running at about 80 hertz on a single core on a laptop, right? So this is, you can run things in real time. And I think my overall argument here is, when people say this, they're used to simulators that do bad things when you take big time steps. And so you need to simulate it like 1 or 2 kilohertz to not have crazy artifacts. And what I'm saying is here, you don't have the artifacts. So we shouldn't need to simulate a humanoid robot at a kilohertz. There's nothing in the dynamics that's that fast, right? And here you can simulate it at 50 hertz, 100 hertz, and it's rock solid stable and doesn't do weird things, right? So I'd argue like we don't need that. And maybe this is an okay, the steps are more expensive, but they're better steps and you don't need as many. And yeah, there's a question I'll take, yeah.
There is another question. Lishkova, please go ahead.
I have a question about your trajectory optimization problem. So you're saying you're using the variational integrator with constraints, but that usually leads to like discrete algebraic equation system, and it's incredibly difficult to solve when you have a new nonlinear problem. Do you do any tricks? Do you convexify the problem in any way to fix this? Because just from practice, I know it's incredibly difficult to find a solution in such case.
So you're talking about DAE's differential algebraic equations when you have constraints? Is that what you mean?
So what you're saying is you have a variational model with constraints, right?
Mm-hmm. Yep.
So that turns into basically a DAE system, and it's incredible. Usually, at least in practice, it's incredibly hard to solve for a nonlinear problem. So I was just wondering if you do any tricks in order to solve it, if you convexify it or you add additional constraints to it.
Okay, so yeah, so there's this is maybe a longer conversation, but basically we're not solving a DAE. We're actually like directly minimizing that action integral. And so what it ends up looking like is actually like a constrained nonlinear optimization problem that we're solving. We're like directly solving that minimization problem. We basically discretize time and then directly minimize. So it's a little bit different than like a classical, more like what I'll say, like a continuous time approach to like a DAE. And essentially, we're just like using standard optimization methods to do this. We throw an interior point solver at it. And yeah, I think like we do not have major issues solving these things. It's basically just Newton's method. And in the simulation context like this, it actually worked great because you can warm start it. So if you take one step, right, you're always starting the next simulation problem, like the next time step, using like the current time step as the guess. And it's pretty, if you're taking reasonable time steps, it's not, the solution's not changing a ton. At 100 hertz, the answer in 10 milliseconds is not that different from the answer now. So it turns out the warm starting is really effective here, and we can generally solve these in like a couple iterations of Newton's method, and it's not super terrible. Hopefully that answers the question. I guess
ask later on again.
Sure. Yeah, happy to try more. And then one thing I wanted to point out that's also really interesting about this. So one way of thinking about this whole setup is I would call this like using language borrowed from like the CFD and FEA communities. I would call this tightly coupled as opposed to loosely coupled. And what I mean by that, in a classic simulation setup, that would be used in robotics, you'd have a collision detection library, right? And that would be doing something like GJK, whatever, that's returning, normal vectors and, signed distance functions, whatever. And then that gets fed into your dynamics and you take a step, right? And there's sort of this one-way interaction between these things. Like, you basically put poses in, get distances and normals out, and that's it. That's a step of the, what we do instead is these things are tightly coupled at this very low level inside the solver, right? And we're iterating with both of these in the loop. And so what this does for you, right? In particular, I'll point out this example where we're tightly coupling the collision detection problem, which again, we pose as this convex optimization problem, with the impact dynamics problem. So where this gets really interesting is if you imagine two blocks with face-to-face contact, that problem doesn't, if you're talking about point contacts where you have just a single point solution for the closest points between these things, in the face-to-face case, that problem doesn't have a unique solution, right? It can be any point on the surfaces, right? So what happens classically is you'll regularize this thing and you'll get like the collision detection solver will basically give you like, say, the centroid on the face or something. It'll pick some random element of the set, right? I'll give you the centroid or whatever. And that just gets fed into the dynamic solver. And it just kind of uses that in a very open loop way. And what ends up happening is the thing on the left here. You get weird kind of non-physical artifacts in settings like this, where you can't stack blocks, for instance. And what happens in Dojo in our stuff instead is these problems are coupled together and they're solved jointly. And what that does for you is, in the collision detection problem, like that on its own does not have a unique solution, right? It's any point on the face between the two blocks, say. But when we couple this into the impact dynamics problem and we solve them jointly, it turns out the impact dynamics, what that's problem's doing, right? It has an objective function, which is minimize, it's solving that least action problem. It's minimizing the action. And roughly that action is like, you know, an energy thing. It's an energy-like function. It turns out when you minimize that energy and you kind of hook those two things together, it turns out that energy minimization objective regularizes the collision detection problem and makes it have a unique solution. And it turns out it's the solution that minimizes the action. And unsurprisingly, that's the thing that minimizes the action is for everything to sit still and not bounce around and do weird unphysical things. So it turns out by hooking these together, you get this very natural regularization and you get things that are physically reasonable out, where it picks the point that is like sort of the point that uniquely balances the blocks and makes them stand still, right? It's just kind of cool that like this kind of tight coupling thing does interesting things. And then lastly, like a kind of a note about the derivatives. I kind of already said this, right? We can sort of back off on the, so here what you're seeing is the black line is the hard answer, fully converged. And then the purple lines are various, those are the iterates as we crank on row at each iteration of the interior point solver, just showing you that you kind of go from this very relaxed, smoothed out gradient to this very steep, you know, basically exact solution. And you can pick any of those purple lines you want as your gradient. And we've kind of played around with this a bit, but I think I don't have anything super rigorous to say about this other than what we do in practice is we return the real, you know, answer for the, say, pose trajectory, right, for the dynamics. And then when we want the gradients for, say, plan and control, we pick one of these purple lines. And in practice, we've played around a bit and we've kind of settled on, it turns out for most of the cases that I'll show you some examples of this next. We found rho equals 10 to the minus 3 to be a pretty reasonable thing that doesn't get numerically ill-conditioned and double precision and gives you reasonable gradients, which is, you know, kind of one of these purple lines in here that's somewhere in the middle. And so examples of what you can do with this, we threw this at all kinds of stuff, right? So the sort of the top left one here is this is a hopper, and this is just throwing these dynamics into iterative LQR and trying to get a hopping trajectory. The block tossing example here is doing system identification, where we're just tossing the block, taking the gradients out of the simulator and trying to fit the block's parameters, like its geometry and mass properties and all that stuff, using the gradients and just doing kind of vanilla least squares. The middle example here is the classic like half cheetah OpenAI gym example. And here we're doing like very dumb policy gradient method, but we're actually using the real gradients out of the simulator rather than sort of a, you know, random searchy kind of thing. And the last one is doing some sample-based planning for a manipulation task where, again, we're using the gradients. Yeah, question.
Scott,
Oh,
please go.
exactly. I have a question. So how does it handle things that might bounce?
Yeah, so this is a fun one that is sort of like I guess a bit of a philosophical sort of argument for me. So you'll hear people talk about the fact that, you know, these are like rigid body models here, right? And like you'll hear people talk about coefficients of restitution and bouncing and like, you know, softness and all this stuff. And I guess I come at this from, I have a stance on this, which is here, this is rigid body dynamics. If I write down that least action thing with a constraint, what comes out of that is perfectly inelastic contact. That's what comes out of the physics. And so that's what all of this is. If you want to model bouncing, there's a really straightforward way to do that. It's to add a degree of, so if I want to model a bouncing ball, what I'll do is make a sphere, and then I'll put like a radial spring in it. And I'll actually explicitly model that spring degree of freedom, and now it'll bounce. And so I guess the take is if you want that behavior, you can put it in there by explicitly modeling it. And personally, I'd rather have that than like a pile of heuristics with like, you know, kind of fudge factors to kind of artificially get it. At the end of the day, what's really going on there, right, is there's deformation and like dynamics that you could get out with like an FEA method and modeling the flexible dynamics. And I'd argue I'd rather like go at that in a principled way and model those degrees of freedom explicitly and have something physical to tune or whatever that's got some basis in reality rather than like making something up, you know. So yeah, you can do it, but you got to model it, essentially, is the deal.
Thanks.
Sure. Okay, and then the last piece of the puzzle is you know, putting all this together and doing control on top of it now. And so we've done this. Here's a couple of cartoon examples. You know, kind of a couple quadrupeds, you know, walking, climbing up on a step, whatever. So you can do this, using standard stuff. This is all done with collocation methods, I should mention, offline. But the unfortunate thing is that this takes these very short trajectories are like 5, 10, 15 minutes to solve offline. They're very expensive, right? It takes a long time, nowhere close to real time. So what we then started looking at, so I should mention, right, the dream here is to be able to do this on the robot in real time. That's what we want to do. So we can do it offline. So then we started looking at, what in this whole setup can we start approximating to do this online. And what we were very much going for was the closest thing to like classic convex MPC that we could get here that still reasoned about the discontinuous contact dynamics. So we wanted to like approximate as much as we could while still retaining like the end goal is to retain the ability to reason about contact modes, right? So here's what we did. So the first thing is we took this optimal control problem, we solved it offline for some gate that we liked, and we then wrote down a tracking cost. So now we're doing reference tracking instead of solving the problem from scratch. So that automatically makes it harder, or just sort of easier. And then what we're doing here, right, inside the control problem now, we have a quadratic cost that's just a reference tracking cost. It's like, squared error from this reference trajectory we're trying to track, right? So that makes that easier. Then in the dynamics, we're going to take that reference trajectory and we're going to linearize all of the rigid body dynamics about that reference trajectory. So what I mean here is we're not linearizing any of the contact stuff. This is purely just the manipulator equation kind of dynamics for the robot, right? So we go in and linearize all of that about the reference trajectory. So now that's nice and simple. Then for the collision detection kind of contact part of this, we go and linearize the sign distance function. Right. So what we've got now is one way to think about this, if you're familiar with kind of complementarity and all this kind of stuff, we basically turned the dynamics into a linear complementarity problem now. So we've linearized all the dynamics, rigid body dynamics, and we've effectively linearized the contact manifold of that phi function, right? So like all the pieces are now linearized, but it's retaining that complementarity, that sort of switching between contact or not contact. And then lastly, we also linearize the friction cone, which isn't strictly necessary because that thing's already convex, but turns out it's a little faster to solve that with a pyramid instead of a round cone, which is a pretty standard approximation. So you go and do all this stuff, and roughly speaking, what this ends up looking like is a quadratic tracking objective, like exactly like you'd see in a classic QP. If you were to do whole body, kind of tracking control, we linearized everything out of QP. This is kind of what the optimal control problem looks like. But then the dynamics constraints are basically a linear complementarity problem. That's sort of where all the pieces have been linearized about this reference, but it retains the complementarity stuff. And it kind of, another way, right? We're retaining the overall block structure here, where each of these is like a full optimization problem with all the constraints and all the nastiness, but we've kind of made the insides of those problems nicer and easier. Okay, so that's the setup. And then there's a lot of secret sauce that it took to get this to work. And I'll kind of try to briefly summarize. Basically, there was like a couple months of really heroic implementation work by my students to make this fast enough to run in real time. And the quick summary is, lots of smart, sparse linear algebra. We end up, like, one of the things we do in my lab is write MPC solvers at a pretty low level. And what that generally means is doing lots of sparse matrix factorizations ourselves and trying to be clever about the sparsity structure in these things. And what ends up happening here that's really cool, there's a bunch of this stuff, like condensing and like sure complement tricks we play, but the kind of the overall like high level trick that makes this work super well, it comes down to you're solving a QR factorization of this thing after we massage it a bunch. And the standard methods for doing QR factorization, there's householder reflections and Givens rotations, a couple standard ways. But what they both do is they kind of, if you imagine you've got your matrix A and you're trying to compute Q and R, roughly speaking, what you do is you walk down the columns of that A matrix from left to right, and you zero out the stuff below the diagonal column-wise from left to right, okay? So in this particular case, it turns out because we went and did all this linearizing ahead of time offline about a reference trajectory, most of the matrices in this whole mess, we know most of that stuff ahead of time because it's mostly stuff that's been pre-computed, like Jacobian matrices for the dynamics about the reference, all that kind of good stuff. So most of the stuff in this big matrix we have to factorize, we know offline, something like 90% of it. And only about 10% of it is actually changing online in real time. So what we ended up doing is we kind of form all these giant matrices that we need to solve. And we permute all the entries. We permute rows and columns in these things to line everything up so that all the stuff we know offline ahead of time is pushed all the way to the left of the matrix. And all the stuff that we need to update online is pushed all the way to the right in the last few columns. And then what we do is offline, we start computing the QR factorization. We pre-compute that factorization across as many columns as we can with all the stuff that we know a priori. And then online, all we have to do is fill in the last few columns and finish the last few columns of the factorization. So it turns out just doing that and like kind of being a little clever about what you know offline ahead of time versus what you need to know online and pre-factorizing as much as we can, we ended up with a 15x speed up. And that's basically the key trick that made this doable in real time. It's kind of like digging really deep into this kind of sparse linear algebra stuff and thinking hard about that. Okay, so lots of crazy heroic implementation work. So here's some examples of stuff you can do with this. There's some toy problems first. So this is something we call PunchBot. It's an inverted pendulum with like this kind of little arm that can push against the walls to balance. And you kind of randomly perturb it, and it's got to not fall over, right? And the setup here is the inverted pendulum is linearized about that vertical upright equilibrium, and that's it. We don't give it anything else. That's the references stand straight up. There's nothing in there. There's no contact at all in that reference. And then we just hit it, and this comes out, right? So when it gets hit, it can reason about putting that arm out and touching the walls to recover and balance. And again, so roughly speaking, this is like a cartoon proxy for push recovery, right? And this has, again, no pre-specified mode information. No contact is in that reference whatsoever, and it just kind of figures it out. So that's kind of cool. Here's an example of that reference tracking that I was talking about on a quadruped. And what we're doing here is initializing this thing with a huge number of randomly sampled initial conditions, and then showing what happens as we roll them all out. And basically just you can visually see that after a few seconds, all those initial conditions converge towards the desired reference trotting gait or whatever. So you get this kind of nice stabilization and convergence behavior. Some examples of throwing model mismatch kind of stuff in here where we've messed with the dynamics of the robot, or we've put this thing on terrain that it wasn't, the nominal gait was for flat ground, and we can put it on weird terrain and it still kind of works. And then this one, as far as the toy examples in sim go, this is probably my favorite and like what I think is maybe the most compelling. So what you're seeing here is a cartoon model of a quadruped. We call this the point foot model. It's a rigid body with point masses for feet, just because it makes the dynamics easier to write down. And what you're getting here is this is the reference trajectory that we've linearized about that's put in here is a trot at the origin. So it's just a robot standing in place trotting. That's it. What you see here, right? And what we do is we start the thing off, then we kick it in the air, and it's going like 1.5 meters sideways and all this kind of stuff flying through the air. And it manages to, first off, recover. It hits the ground, it figures out, contact, foot placement, all this kind of stuff, where it needs to put the feet to not fall over. And then it trots back to the origin in a very sort of sane way and ends up, now tracking that reference at the origin. So this is like, I think what this is really trying to get at is how those linearizations and approximations in that problem end up playing out and like how valid they are. And so you can see here pretty clearly, right? This is doing a whole lot of kind of contact mode discovery, doing weird things that were not in the original contact sequence, flailing around midair, and then just nicely trotting back to the origin to get back to that like reference. And it's all just that, all that's in there is that periodic gait as the reference at the origin. So for me, this is like really impressive that it can kind of reason about all this and figure all this out from just that. And I guess, yeah, at some level, the spiritual guide here is convex MPC, which we do all the time for smooth system, which is super effective, right? And works in insane settings where you wouldn't think it would on nonlinear systems. And we've done a lot of this in my lab. For example, using on drones, we run convex MPC on drones where we use dynamics that are linearized about a hover. And you could do surprisingly acrobatic things on these where you're still using that linear system that is just linearized with the hover, right? So I think you can do a lot with linear systems, I guess is kind of that. Okay, and then we put this on some hardware. I would say these things are not crazy impressive, but versus the state of the art, but it does work. We can run these things fast enough to actually put on hardware. That's the trotting controller on the quadruped. And then one of the more interesting things here, right? So obviously, stuff like MIT cheat is way more impressive than this, right? And they're able to solve these problems much faster, and they've got really well-tuned heuristics and things. They've been doing that for a decade, right? So it's really good. It's much better than this. But one of the things they can't do that's kind of interesting is, this, we can plug in an arbitrary motion and it'll just track it, right? So we don't need to track, for example, a periodic gate, a trot, any of that. You can just give me something. And the other thing is that it can reason about contact with arbitrary parts of the body. Doesn't have to just be point foot contact. So this was trying to get at some of that, where we're like making contact with other parts of the body, just tracking some weird arbitrary thing that's not periodic. And yeah, there's more to do here for sure, but kind of interesting that yeah, the dream is you design some offline reference thing, anything you want, just throw it on here and it can track it. Okay, so some other just kind of like final summary things, some pointers into what other things we're looking at, some connection stuff. So turns out that this whole sort of composable optimization approach has lots of connections to lots of other things. One area is game theoretic planning control. It turns out that the setup we're doing is actually strictly more general than, and sort of subsumes both Nash and Stackelberg equilibrium problems from game theory. And that's actually where a lot of this stuff started. We actually ended up, at one point we were doing like MPC. We did game theoretic MPC for driving to like reason about interactions between drivers. And like it turns out you can model that like Nash equilibrium problem very nicely fits into this framework, and we can use the same solver tricks. And then sort of if you're familiar with classical robust control and kind of these adversarial ideas, it's also an instance of one of these composable optimization problems where you have your like optimal control problem and then your like adversarial disturbance problem that's trying to maximize the cost, and they're kind of fighting each other. Very much has this structure of like, coupled optimization problems, and again, fits into the framework, and you can use the same tools to get at it. So there's lots of other things I think that this composable optimization setup can be used for. They're kind of cool. And then like high level, kind of thoughts on where I want to go with some of these tools. And one of the things I think is interesting at a maybe a little more philosophical is that, we hear a lot about the sim to real gap, especially among RL folks, right? And there's been a lot of work on transfer learning and trying to get things to, you pre-train in sim and then go to the hardware. And one of the things that I think hasn't really been taken seriously there is I think most of the people doing that stuff haven't taken simulation and simulators seriously enough, right? We've heard a lot about differentiable simulators too in the last few years, and actually, hot take, there are no differentiable simulators, right? Like all the people that claim to have a differentiable simulator, there's discontinuities in there somewhere. In particular, right, like the collision geometry stuff that we mentioned, like this GGK stuff, everyone's using that stuff, and that's very much not differentiable. So even if they've got some like smooth contact model, the underlying geometrical stuff that they're doing is not differentiable. So there's fuzzy weird stuff in there. But then yeah, kind of the bigger picture argument here is that like if I go run this stuff on the hardware and I get some data, why am I not currently able to take the data I collect from a real hardware system and pull that back into the simulator and improve the simulator so that I don't have to do transfer learning next time, right? And so like kind of one vision for doing this is, you can imagine, if you have the simulator and you have the real robot, and the areas where maybe the model's bad, or like, you can do some experiments and do some error analysis and figure out, oh, maybe there's some compliance in the legs. My actuators are not perfect torque sources, go figure. And there's like motor dynamics and power dynamics, weird stuff going on there. And then the classic one is, friction models are terrible. Coulomb friction isn't real, that kind of stuff. And then maybe even like some of this collision geometry stuff. Let's say you kind of think there's problems in all these places. You could imagine taking the simulator and then inserting parametric models or even black box function approximators like neural networks in strategic places where these things show up in the dynamics, and then fitting those either parametric models or function approximators to data from the robot. And having a simulator like this where you can take the gradients of everything and do least squares in a very straightforward way, it kind of enables some of this, right? So I think the idea of like more tightly integrating the simulator with the hardware that you're actually running and with the hardware experiments, right? And trying to pull data back into the simulator in a straightforward way, I think is potentially really powerful, and maybe a way of kind of reducing the sim to real gap sort of thing. Another way of saying is that we should be doing real to sim transfer. We should be taking the real stuff and trying to pull it back into the simulator. And then another thing that we've been working a ton on recently in the lab, and it's been a long theme, but we finally started to make some real progress on it in the last year, is trying to scale a lot of these algorithms. So all the stuff I showed you, right, all this context implicit stuff, all of the MPC stuff I showed you, I would say to first order, all of that is basically serial and runs on a CPU core. And there's some stuff in there that we can parallelize, but for the most part, you know, a lot of these algorithms are just inherently serial in a lot of places and a lot of ways. That's frankly annoying. And so it's super hard to parallelize these things. So we've been working hard on ways of trying to take advantage of GPUs and throw thousands of cores at some of these problems. I think the promise is there, like the compute's there. And I think in particular, right, the machine learning community learned this lesson a long time ago, and they've had huge strides in this and just taking advantage of these computing resources that exist now, right? And I'd say on the model-based control side, we've not done that, right? Most of the MPC stuff is still running on a single core. There's just, it hasn't happened, right? And so that's just at a high level. We're working on this. We have a couple papers we just submitted to ICRA actually on this topic. One, we managed to get a QP solver for doing MPC running on a GPU, and I'll just tease the result, which is this is taken from the paper in the bottom there. We managed to run a whole body QP stabilizing controller for the Atlas robot balancing on 1 foot and like prodding it and having it wiggle around at 2.6 kilohertz sample rate by putting it on a not even a super high-end GPU. So there's like huge potential there, I think. Okay, and I'll stop talking with that. I just wanted to plug a handful of students who've done all this work. The top row here, Taylor, Simon, and Brian were the heavy lifters on most of the work I showed you. And they've all graduated in the past 6 months or so. And then the bottom row, Kevin and Shro's about to graduate. He actually just started working at Tesla in their humanoid group a few months ago. He hasn't quite graduated yet. Kevin's still with us. And then Chian was a master's student who did a lot of the hardware experiments that I showed you on the quadruped, and he's moved on too. So that's about it. And yeah, love to chat more with you guys.